Okay, so hello and welcome all of you for today's session on quantum mechanics. So today what we are going to do, we're going to basically continue our discussion which we started in previous two lectures, in which we started with the commutation relations and then we arrived at what we call as operator algebra. So operator algebra of two quantum mechanical systems. One of them is quantum harmonic oscillator and another one is uh, angular momentum. And from the angular momentum we also were able to arrive at the algebra of Pauli spin matrices, and which is going to be the focus of our today's session, because Pauli, what we call as Pauli matrix formalism, is very fundamental to quantum mechanics. So therefore I think if I have to identify this one of the central pieces of quantum mechanics, I would say Pauli matrix formalism will be one of them. Okay, so and we are going to look at various aspects of why it is important, because typically what the way we get introduced to Pauli matrices is from the point of view of the spin. Okay, so so we get when we start studying spin angular momentum, and that's when we get introduced to Pauli spin matrices. Okay, where the identification is that each for each spin component, the corresponding observable is given by a Pauli matrix. Let's write the correct identification. The identification is that for every spin component, like a spin is going to be an operator here, it's an observable, so it's an operator here. So for each one of them we are going to have an operator, and the Pauli matrices multiplied by corresponding correct physical this constant, Planck's constant, gives the correct dimensions, and then we have these matrices. So this is the identification between the spin and the Pauli matrices, and that's how we get introduced to uh, Pauli matrices. But that's not all. Let's make it very clear right at the beginning. That's not all. It's not just because of the association of Pauli matrices with spin angular momentum. That's why they are important in quantum mechanics. But there are many other aspects where Pauli spin matrices become important. You may be dealing with a quantum mechanical system which has nothing to do with spin, and still you will be using Pauli matrices. I think this is going to be new for you. So let me go slow over it. Okay. So but before I go on to that, let us complete that the spin angular momentum. We represent them. How do Pauli matrices enter in quantum mechanics? The way they enter is that when you represent your spin operators, you can represent them in terms of Pauli matrices. So each Pauli matrix represents the observable of the associated with the spin. Okay, then we also saw they satisfy the same, because they are angular momentum, they represent angular momentum in quantum mechanics. Therefore naturally they will satisfy the same commutation relationships as that of angular momentum. And for angular momentum, if we remind ourselves, we can write down if we write down the general one, so we will typically write them in a more nice form, like let's say we write it L. There's an epsilon also, to be more precise. So we'll write it epsilon k, then we will have a summation over I and j. So or in other words, if we write it in a very simple language or in more explicit component form, we remind ourselves that we had this Lx operator and then Ly operator. It used to give us I times Lz operator. Fine. So that was those were the relationships for angular momentum, and we have derived them. We have derived these relationships, and we know they come from the starting point is always the Heisenberg's commutation relation. So this commutator which we have, it can be always. So therefore I would not call, that's why we do not call this commutator as fundamental commutator. Rather we call the Heisenberg's commutator, the commutator which Heisenberg found for X and P type operators. That commutator is called a fundamental, because that's where from we can derive all other commutators in quantum mechanics. When I say all, by all I mean all those which have a representation in terms of position and momentum. So similarly, what we found last time, that using the fact that spin is also angular momentum, so we can do this identification that we will have let's say Sx and Sy operators, it's going to give us I times Sz, with the difference that we have the 2 factor here. So the 2 factor here, it has something to do with spin. We will explore it, but you can also think why this 2 is coming here. You can also mathematically you can see the reason is coming from here, because we define S operator as h by 2 over here. So 1 by 2 is coming over here, and to make it satisfy the same commutation relation as that of angular momentum, we have to multiply by 2 in the spin case. Okay, I think that's the mathematical reason. But the physical reason is that, as you know, the spin degree of freedom always comes with, it's always double. You have the two, you have that 2 levels. I mean, either it can be up spin or it can be down spin. So it has this 2 has something to do with that degeneracy, I would say. Okay, spin always comes with that intrinsic degeneracy, and this has the physical reason why 2 is coming over here, is that it is associated with the double degeneracy of the spin operator. And for a mathematical point of view, it comes from the fact that we do 1 by 2, we multiply it by a factor of 1 by 2 over there. Okay, and that's why and in case of angular momentum commutation relations, we do not have such a factor. So therefore, to make them same commutation relations as that of angular momentum, we have this extra numerical factor coming in. Okay, so anyways, so that's but we do see that for the spin also we have the similar commutation relations as that of angular momentum, and we last time gave a name for those of you who want to explore in further. So the commutation relation which I just wrote is called it's called SU2. Let's write it this way. It's called SU2 Lie algebra, and this is going to be very important when we later on at some point of time have discussions about the conservation and the symmetries in quantum mechanics. And earlier when we talk about this particular commutation relations here, we get something called SO3 Lie algebra. Okay, even if these commutation relationships look very similar to and that's why they are more or less mathematically we call them homomorphic. So they are mathematically homomorphic to each other. However, there are subtle differences, as I mentioned in the last lecture also. There are subtle differences between the commutation relationships of orbital angular momentum and commutation relationships of of the algebra, I would say, rather algebra of the spin operators. Okay, and we are going to, those differences we are going to focus on, and I think last time I just mentioned one of them. So now today we are going to explore them further. So this part is, I think, clear. Why is it that a spin operators satisfy these commutation relations, and how do we derive them if I have to derive them? So the journey towards those commutation relationships is that you start with Heisenberg's commutator, then you define angular momentum as there's a as I said last time, there's a definition of angular momentum in quantum mechanics, what we call as quantum angular momentum. And quantum angular momentum is defined by commutation relationships, unlike classical mechanics, which is defined by classical angular momentum is defined by a cross product between two vectors, position vector and momentum vector. In quantum mechanics, because of the uncertainty principle, we will not be able to use this definition. So therefore, what we do is that we use so what we have in quantum mechanics for quantum angular momentum are the commutation relationships. And as I told you, so this is interesting to note that in quantum mechanics we did not intend, it was not our intention to bring in some algebras over here. However, just by following the Heisenberg's uncertainty principle, we arrived at something called SO3 Lie algebra automatically. This is a very, very interesting point over here, that when you start dealing with angular momentum, you automatically arrive at something called the algebraic properties of angular momentum commutation relationships. Okay, and it's also interesting to note that when you study quantum mechanics, you will see you can notice it very clearly that the subject becomes the whole formalism of quantum mechanics is algebraic heavy. It's an algebraic approach to the quantum systems. While as if you remind yourselves of classical whatever, you take either Newtonian formalism or you take Lagrangian or Hamiltonian formalism, in all of them you see you are mostly relying on the assumption is that you have continuous functions, then you have derivatives, then you have differential equations. That is the kind of algebraic structure, not algebraic, mathematical structure which you use there. But in quantum mechanics, when you start doing quantum mechanics, the formalism itself always is very algebra heavy. It's an algebraic approach, and this is not just for no reason. There are There are very important reasons. So one of the reasons is that the Heisenberg's uncertainty principle itself is a statement. It's an algebraic statement about quantum systems. It talks about non-commutativity of the quantum world. Okay, and that itself is an algebraic statement. Okay, similarly, if you talk about principle of linear superposition in or a quantum superposition in quantum mechanics, that itself is something. It's a statement about algebra. It's an algebraic statement, and it brings in algebra. Okay, so therefore this is to be noted that the reason there is a lot of algebra in quantum mechanics is for these reasons, for physical reasons, that the only way we can describe these principles of uncertainty or principle of linear superposition or other interesting things in quantum mechanics, or the non-commutativity of quantum mechanics, or the fact that you can have these quantum superpositions, all of them can be represented only if we do it algebraically. Okay, that's why we use a lot of algebras over here. Okay, so but as I would still like to emphasize that even though you see lots of algebras, you see something coming in harmonic oscillator, something coming in angular momentum, some algebra coming in Pauli matrices, but I have always been trying to tell you that all of them can be basically brought down. You can trace them back to Heisenberg's commutators. So if we are very well versed in Heisenberg's commutators, it should not be difficult for us to deal with other kind of algebras. Okay, so that's what today what we are going to do is we are going to explore these Pauli matrices slightly in a more detail, and rather taking a different kind of an approach. So I want to divide it in this way. I want to first of all just talk about something we call as two-level systems. Okay, now these two-level systems are the basic quantum mechanical systems which have the full richness of quantum dynamics, plus they have the simplicity of having small finite dimensional quantum Hilbert space. So they have the full richness. They are, I mean, if you study these, this is a very special class of quantum mechanical systems. Okay, very special class of quantum mechanical systems. And in fact, the spin half system, spin angular momentum, what I call a spin half system, that itself falls under, that itself is a two-level system. What do we mean by two-level system? Two-level system is any quantum system which has only just two, its state space is just two-dimensional. It can have only two states. Let's take the analogy from spin system. So it can have only two states, either it is up state or it is spin down state. So such a quantum mechanical system is called a two-level system. It is very simple, just to two states, that's all. But if you look at the dynamics, the kind of stuff which happens in a two-level system, you will find it as rich as many other interesting quantum systems. Okay, so therefore it is very obvious that physicists would have studied these systems in detail, and that's exactly true. That physicists have done a, so this is like the main, like as in classical mechanics, we study harmonic oscillators a lot. In fact, we study harmonic oscillators. They are the best friends of physicists. Why do we study these simple systems? Because these simple systems, once we understand, they can be fully analytically solved. We can mathematically solve them completely, and then they act as a guiding, in some sense, for a guidance for us to deal with those systems which are very complex, which are not very easy to deal with mathematically. That these we take our guidance from these simple systems. We see what happens in simple systems, then we take our guidance and we start trying to understand more complex systems. So that's why I think it should be very clear to you why is it that we should be focusing a lot on two-level systems. Okay, and now what is very interesting to note, that if you take any two-level system, you will always, I will make a statement first of all. In fact, there's a theorem, mathematical theorem also. So but let me make it just a statement. So I will say that any two-level system can be always studied by Pauli matrix formalism. So this is a very general, and I would say very powerful statement as well, that whatever two-level quantum mechanical system you have, you can always map it mathematically. So you take a two-level system, you can always map it, this your two-level system, to a Pauli matrix problem. So which means if you just understand Pauli matrices, you can understand all of the two-level systems in quantum mechanics. As simple as that, and as powerful as that. Okay, so what are the examples of two-level systems. First two-level system we have already talked about is the spin system, is the Spin-Hop system, which we will explore today. So this is the Spin-Hop system, but this is just one example. You can have any, let's say you have a we can take another important example, which is a fundamental, which is called a qubit. You would have surely heard about a qubit. So qubit is the fundamental unit of quantum computation. In a quantum computer, that's where you in a quantum computer, that's the fundamental unit in which you store your information. Okay, now everything about the qubits, okay, is encoded. So how do you study qubits? Qubit is also a two-level system, as you would understand. Qubit, we can, rather than saying it up and down, we can just say it in the logical language, it's 1 and 0. As in a classical computer, we have one state, there are two states, digital states or logical states. We have a logical 0 and we have logical 1. Similarly, in quantum computer, we have these two states as the basic states. Then we have, in quantum mechanics, because this quantum superposition is available to us, we have lot of many other entangled states in between. Okay, so in that's why, and then the whole full sphere of all those states is called a qubit. However, the basic states is we have a logical 1 and logical 0. That's where you start. So if you know polymetrics formalism very well, you will be able to understand qubits and their and the quantum computations which we do with them, because quantum computation is ultimately only two things. You have qubits, then on top of them, in fact it's three things. You have qubits, plus you have quantum gates. Okay, and quantum gates, I will also just give a brief definition. So qubits, quantum gates, and then the third thing is observation, because without observation we do not get the results. Okay, so this is what any quantum computer, you would have heard of quantum computers, any quantum computer has this stuff in it. Okay, so what happens is that, so you have a qubit will be any two-level system. So that's why you hear about something called a superconducting qubits, NMR qubits. You hear about ion traps. Okay, you hear about what are the other examples? Magnetic systems. Okay, similarly nitrogen centers. So you, all these systems, whenever you can do quantum computation only with those systems which are two-level systems. So two-level systems are fundamental to quantum computation. In quantum computation, we do not use systems which have infinite dimensional Hilbert space. We don't deal with them. Okay, we deal, because we have to store information, and for that we should be able to map it to logical 0 and logical 1, and those systems are called two-level systems. So you can understand the whole area of quantum computation is about two-level systems. So here in quantum computation, it does not just become just a simple system. It's not just that it becomes physically important, because that is how you would encode your information in a quantum computer. Okay, so once you have this qubit, what do you do? What quantum gate is, as you would have already heard about these things, something called any unitary transformation in quantum mechanics can act as a quantum gate. Okay, like as we have gates in classical computing, similarly we have quantum gates. And what are quantum gates in quantum mechanics? What are in quantum computation? So they are always unitary transformations. So any unitary transformation or in quantum gates can be always mapped, or basically they are not mapped, they are same as unitary transformations. So you have qubits, which you know now they belong to some vector space, on those complex vector space, and then on those complex vector spaces you do these unitary transformations. These unitary transformations are the gates. And I'm not sure whether you guys know the first three important gates in quantum computer are Polygates. And what are those? The Polygates are sigma x, sigma y, and sigma z. You would not have realized this thing, but polymatrices are also the unitary. They are the gates. They are the quantum gates in a quantum computer. So fundamental are these polymatrices. They are like the fundamental fabric of, whenever we do quantum stuff, you will end up looking at the polymatrices. They are much more fundamental than you would have ever imagined. They are so fundamental. And one example, I don't think I can give a better example than talking to you about that polymatrices. Not only here, when we talk about polymatrices as quantum gates in a quantum computer, they have nothing to do with spin. It's not necessary. You may be using superconducting system as your qubit. It has nothing to do with spin. It's a superconductor. but then when you act on gates on that superconductor, you will be using polymatrices. Okay, so I think this is one of the most concrete example of how fundamental polymatrices are. And the question is that there are two questions now. One, why is it that, what is it in these matrices? They look so simple to me. They're just ultimately at the end of the day, they're just 2 by 2 matrices. What is it in that matrices that makes them so fundamental? That's question number one. Second question is that if they are so fundamental, how do I make sure that I am very comfortable with these matrices? I just do not, I just want to master them. I just want to become very comfortable with the, understand them both physically, physics level, as well as quantum mechanically. Okay, then so you can see this is these are like spin system separately is a 2-level system, then qubits in quantum computer. But qubits we can have qubits in different ways. We can implement them. As I said, we can take a something called a Josephson subjunction, which is a, we can model it as a some kind of a 2-level system. Similarly, many things in chemistry can be modeled as a 2-level system. And I think more importantly, anything which you start with in a quantum computer is a 2-level system. You can always represent it. The standard, the only way, I would say, one of the best ways of the in physics of representing qubits and the quantum gates on them is in terms of polymatrices. Okay, so I think this part was to tell you, because I was not sure that you would have thought about polymatrices in terms of 2-level systems, because typically when we talk about polymatrices, you always think of polymatrices as something to do with spin. So today I'm telling you that it's not true. It's not the entire story about polymatrices. Polymatrices formalism is much more general than just talking about the spin itself. Okay, now let's get straight to the question of what is it inside these matrices. Okay, so to understand that, we will do something. We'll do following. We will just look at their algebra first of all. So as I said last time, polymatrices just do not satisfy angular momentum algebra alone. Rather, they have one more, then they have a rather more richer algebraic properties. So let's look at them, some of them. Angular momentum part we have already looked at. So the polymatrices also satisfy, I will write it first in a simple way. So they have these interesting properties. Just first of all, just look at this equation. Just think of those matrices. Have you ever thought there can be a matrix, if you square that matrix, it gives you unit matrix? Just look for examples. Look for examples. I mean, remind yourselves from your course in matrices. You will see matrices are basically inside the matrix. There are numbers. Some of them may be 0, but most of them are not 0. And if you square them, or square the whole matrix, it becomes very difficult to understand why will it become unit matrix. Okay, it's like this. I give you a number, any number a, and I'm telling you I square it, and it's giving me unity. Fine. So it's very difficult to understand how is it possible that you give me, I take a number, and if I square this number, it gives me unity. Fine. So these kind of algebras, the kind of these algebraic properties are very important. They are very counterintuitive. How is it that they give us these properties? Okay, it's along the same line as like as when we were younger, we used to look at this iota square, and gives us -1. It is one of very interesting, I would say, examples. I mean, you square any number. Let's say even if you treat this one as a number, we call it imaginary number, and you square this imaginary number, it gives you -1. That's not what usually happens. If you have a number, it gets squared. If I have 3 number, it gives me 9. If you have 4, it gives me 16. I always get bigger numbers on squaring. I don't get smaller number. I don't get 1. It's very counterintuitive to me. Why is it that I get 1 out of squaring it? So that's why these, I mean, this is just to hint to you that there is something going on over here, and we have to understand that. And then even more interesting thing is that why is it that in such numbers are then arising in quantum mechanics? Okay, so what exactly is going on over here? So we will try to demystify it a little bit. We will try to see whether we can make sense of it. But I just wanted to because in our many algebra courses, in our courses on mathematics, many times they don't focus, they don't emphasize on these things which are very important in quantum mechanics. And another property of these matrices is they have this very interesting property. They anti-commute with each other. You take any two of them, so you take any two of them, they anti-commute with each other. Fine. So then similarly we will have y and z, then we will have x and z. Okay, so this is another set of their interesting properties. One, they always scale to unity. Then among themselves they anti-commute. Anti-commutation is a special form of non-commutativity. It means they are not commuting with each other, but they are after when you try to commute them with each other, when you try to commute them, reverse the order, they pick up in physics we say they pick up a minus sign. So among when you change their order of the matrices, they pick up a minus sign, and this minus sign is so fundamental in quantum mechanics. It's very fundamental. It is the famous negative sign of quantum mechanics, famous negative sign of fermions. It has something to do with, you would have studied in quantum mechanics, something to do with antisymmetric nature of the wave functions which you write for wave for the fermions. You remember in the fermions you have this kind of a equation. If I write down a wave uh, wave function for a fermion, and if I interchange it under the, I change these coordinates, I make it y and x, okay, or rather say x1 and x2 here I become x2 and x1. So it picks up a minus sign. The wave function of the fermions is antisymmetric, while as a wave function of the bosons is symmetric. Okay, this negative sign you see always coming in, and it is physically it is the same negative sign which comes over here also. I mean, we will have to get into the explanation how it is so, but you just trust me for time being that this is basically the same negative sign, because both these systems are related, fermions and spinors. Okay, now this is the third this is the second property, that so if we put both these properties together, so I can write them in a more concise way. I will write them this way. So I'll write them sigma mu and sigma nu, I'm sorry, is equal to 2 times delta mu nu. This is how we write it. Okay, so what it means is that if mu nu, okay, let me expand it first of all. So sigma mu, this is called this curly bracket over here is this is the symbol for anti-commutator, and anti-commutator is written as sigma nu, then plus, not the minus. In commutator you have a minus sign, in anti-commutator you have a plus sign over here. Then we have a sigma mu and sigma nu is equal to 2 times delta. This is the Kronecker delta, usual Kronecker delta. Okay, so now if we expand it a bit more, so what it gives us, that let us say we have sigma is mu is equal to nu. In that case you will see this becomes same, and then it gets just repeated, so it will be 2 times of that. You will have basically the same stuff. So but as we know, this is like 2 times of sigma mu square, so that gives us 2. Okay, and if mu and nu are different, then it does not square. Then what does it give us? Then sigma mu and sigma, let's say sigma x and sigma y, then we will have plus, then we will have sigma sigma y and sigma x, let's say. Well, let's see what it gives us. But we know that they have these anti-commutation properties, so it means that it will give us sigma x, sigma y. We will have, it will be minus times sigma x, sigma y, because they have anti-commutation relationships, which means it gives us 0. Okay, so if they are same, if the indices are same, it gives us 0. If the indices are same, then it gives us 2. If the indices are different, then it gives us 0. Okay, so this set of algebraic properties what I wrote it here, that if you square them, that they give you unity, and if they are different, that gives us 0, and they have this 0 is because of the anti-commutation. So this set of properties, it has a name in mathematics, and it is one of the fundamental algebras in mathematics. It's called this set is called this set of definition, this set of properties is called Clifford algebra. And if you look for your quantum mechanics books, I don't think, I'm not sure, at least the ones which I have studied, the very popular ones, they don't discuss about Clifford algebra of the polyspin matrices. They don't deal it, and that is the missing link, because they do not tell you the entire story of the Pauli matrices. It looks very mysterious. Why is it that these matrices have these numbers into it? Why is it that they are behaving like that? So, but we can make sense of it. I mean, if we want to really get into the details, we have to look into Clifford algebra. However, at least I have told you that the polyspin matrices are not just rotation matrices. They have more interesting they have more properties, and because of those properties, because they are satisfying these Clifford algebra relationship, in addition to I would say to the rotation matrix, rotation properties or rotation commutation relationships. That's why they have these properties. Okay, many of these properties can be easily now understood. Okay, so they are anti-commutativity. Now what is Clifford algebra? General Clifford algebra is like that. You have any, let's say, gamma, mu and gamma nu are the generators. Then they have this anti-commutator relationship. Let me write it this way. So this is the general definition of Clifford algebra. In terms of the generators, you have gamma, mu and gamma nu, and they satisfy this relationship. So any set of set of operators which satisfy this relation, they are satisfying the Clifford algebra. This is the property of the Clifford algebra. Okay, and I'm not very sure, but there are some number systems which satisfy these properties. One of them is which is called a quaternion. I don't know whether you have heard of these. It's not very important for our discussions, but I just wanted to mention them because they are also very important. So there is a system of numbers. I'm talking about numbers. The way you have complex numbers, you have real numbers. Similarly, there's a number system called quaternions, and they were also discovered by developed by the same Hamilton who gave us Hamiltonian mechanics. The same Hamilton gave us the quaternions. Okay, and they are very, very important when you talk about rotations. Okay, and they are also related to the Pauli matrices. That's what I would say. And this is one example. Quaternions is one example which satisfy these Clifford algebra. And what I'm trying to say over here is that Pauli matrices also satisfy the Clifford algebra, and those mysterious properties of Pauli spin matrices is because of their Clifford algebra. Okay, now let's keep on continuing decoding it. Okay, now we found that Pauli matrices have many interesting properties because they satisfy Clifford algebra also. And then now let us look at where are those numbers coming inside the Pauli matrices, because Pauli matrices, what are Pauli matrices? Now we also understood the Pauli matrices have two aspects now. One aspect is that they represent for us the spin angular momentum, and that part is pretty clear to us now because we know where from we got our commutation relations of angular momentum, and exactly same way we can say that a spin angular momentum also satisfies the same commutation relation. So we can write down spin angular momentum commutation relation. That part is now clear to us. But we also understand that Pauli matrices are also something called a representation. They are the matrix form of what? Clifford algebra. So this is something which is not discussed in your textbooks, and this is the, I think I would say this part is really, really more important for especially for those cases where we use Pauli matrices, but we are not dealing with spin as such. We are not dealing with spin angular momentum, but still we are using dealing with the we're using Pauli matrices, especially as I gave an example of qubits. In qubits, they may not be, as I said earlier also, they may not be qubits, not necessary it's a spin system always. It's not necessary. You can make qubits from different systems, but you still use Pauli matrices. Why so? Because in qubits they will satisfy these Clifford algebra. I think this is one of the fundamental messages of today's lecture. And those of you who really want to take it forward, the quantum mechanics, and take their career ahead in quantum mechanics, I would rather tell them you just take this point very, very seriously and spend your time on exploring this direction a lot more seriously. And you can surely, because I mean your textbooks don't talk about Clifford algebra. In this lecture we have talked about it, so you can always come back to us. We can have more discussions, get in more details, but I found it necessary to tell you the entire story about Pauli matrices. Okay, so going forward, I just want to do some sort of a calculation here. So let us, now we know we have three Pauli matrices: sigma x, sigma y, and sigma z. Now what we want to do is that we want to see how do we get something called till now we were just looking at their algebra. Now we want to get there something called a matrix representation, and calculating matrix representation is one of the important questions in quantum mechanics. How do we get given an operator? Let's say you are telling me that this is angular momentum, it satisfies these commutation relationships. How, for a given quantum system, how do I get how do I get those matrices? So that's an important question in quantum mechanics. So how do I get a matrix representation of Pauli matrices? They basically satisfy these algebras which we know, but how do we get it? So to do that, and this is very important, how do we get those numbers there? So how do we get the general question? How do we get matrix representation for any operator. Let's say we have a is a general operator. Let's say for simplicity it is just a two level system. It's just a 2 by 2 matrix. So these guys, these elements there inside the matrix, they are called, as we know, they are called matrix elements. Okay, how do I get matrix elements in quantum mechanics? So to get the matrix element in quantum mechanics, you need two things. You need a vector space. Without a vector space, you cannot get a matrix representation. So my A11 is basically, this A11 is basically, I have assumed, I have taken some basis, let me call that some psi, and I am basically calculating the effect of action of A on psi. Then this is giving me that A11. Okay, so similarly, let me call that I may have a basis, so which means it will be psi1 and psi2. It may be some, in our case it will be just two-dimensional basis, so I will have psi1 and psi2 as just two components. So similarly, my A12 will be psi1 A and psi2. Psi1 and psi2 are two basis elements of the vector space, okay, because we are dealing with two level system. And then here I will have psi2, then A acting on psi1. Same goes with A22. In A22 we will have psi2, then A acting on psi2. So what is happening here? What's happening? This is how you determine any matrix representation for any quantum mechanical system. So you can, it's not true just for two level system. For two level system we can write it down complete elements, but for a higher dimensional system also you can use the same. That's how the definition of a matrix representation is. That's how you determine. So to get matrix representation, before you start getting matrix representation, you have to get the vector space. What is the basis you have chosen? So you choose a basis, then you see what is the effect of those operators, that operator for which you are looking for a matrix representation. So you say, it is in mathematics we call it action of this operator on the wave function, on that basis element. Okay, so you calculate, you should know two things. One is the basis. To get a matrix representation, we should know two things. One is basis, then second thing is action of the operator on the basis. Action of operator on basis. Okay, so we will see for Pauli matrices which satisfy these, we will do the same thing. Okay, now let us choose a basis. We will choose the simplest basis which we have. So the basis is, let's call that by basis psi1 is our basis is 1 and 0. This is going to be our basis. Then psi2 is going to be our 0 and 1. This is obvious. This choice of this basis is very obvious because we have only two states. This means the up state, this means the down state. Okay, physically this means up state and this means the down state. That's the basis we have chosen. Fine. And now what we want to do, we want to get these elements for Pauli matrices. Okay, before I go there, so basis is chosen. Now what I also want to define the effect of the and let me write down them in some cat. So I am going to use this cat notation over here. Okay, so let me take this sigma z and let's see what is the effect of this on this one. So sigma z is going to, and we have also made this choice that sigma z is going to be the direction, this is the direction of the rotation. Okay, so which means sigma z will act on spin. It's going to give us 1 and then it's going to leave it like that. In fact, it's just going to leave it like that, then it basically means it's getting multiplied by 1. For the sigma z, when it operates on down basis, it basically means it is in the down direction. How do we see that? It gives us -1. That is the down direction. Okay, so these are the two relations which tell us how is sigma z operating on this basis. So it also means, as you can see, that it is giving us these eigenvalues. It means in this basis which we have chosen, sigma z is diagonal. So it is diagonal. It is, which also means that it is, we already know the eigenvalues of sigma z. Because how do we do that? Because we have already chosen sigma z axis as our axis of rotation. Around that there is rotation happening. Okay, so we have made that choice and we have chosen this basis. Now we can go ahead and write down the matrix for sigma z. How do we do that? So now our sigma z matrix will be, I will write it, let me just write ij just to tell you that these are the matrix elements. Okay, so what it will be up state, then sigma z, then up state. Okay, then here we will take up state, then sigma z, then down state. Okay, then here we will have down state, sigma z and up state. Then here we will have down state, sigma z operating on downstate. Okay, so that's our matrix representation of it. Okay, and now let's see. There is also that we are using orthonormal basis, which means that, as we know, orthonormal basis will mean for us, if I have psi I and psi j, they are basically orthonormal. That's what we are using always in quantum mechanics, and the basis which I have chosen is already orthonormal. So that assumption, that thing is there. So sigma z, when it operates on 1, it gives me 1, so it will give me sigma z operating, it gives me 1, so I will get this stuff. Then sigma z operating on downstate, it gives me -1, that will come out, and I will get this stuff. Then sigma z will operate on upstate, it will give me 1, so I will get this state. Then I will have sigma down, and sigma z operating, it gives me minus sign, and it gives me this thing. Okay, now let's see what do we get out of this matrix. These matrix elements are there. So now what do we get? We'll see. So because of the orthonormality, this is going to give me 1. It's the same state, so it's going to give me 1. Okay, now here this up and down state, these are two states. We have just two states. Because of the orthonormality, this is going to give 0, because they're orthogonal with each other. So if I take scalar product, it's going to give me 0. As we know, if you take scalar product of orthogonal vectors, it's going to give us 0. Here it's going to give -1. Here we get our sigma z. So sigma z, this is the matrix representation of sigma z. Earlier we were just talking about properties, algebra, what's called algebra. So there are two things. One is the algebraic properties, let's say commutation relation is. One is the matrix representation of that algebra. Earlier we just said that sigma z square is to 1. That was one of the properties of which sigma z satisfies. Here we have at least one of the matrix. We can have another matrix representations also, but this is one of the matrix representations for the Pauli matrix, that it will always be 1, and we can also see it's diagonal, which means the basis which we have chosen is the eigen basis for sigma z. Physically, what it means? Physically, it means that rotations are happening around the z-axis. That's what it physically means. Okay. So now we get onto the other two matrices. What about sigma x? Okay. Now to get the matrix one, same, we will follow the same approach. So our sigma, it will be we will have same thing. Instead of sigma z, we will have just sigma x now. So we'll have up and then sigma x, then up. Okay, and then we will have other elements. Let me take them here. I will have here up, then we will have sigma x, then we will have down. Fine. And then same here, we will have down sigma x, then we will have up state, then we'll have down sigma x, and then we will have down state. Okay, now to determine these, we should know what is the effect of sigma, what is the action of sigma x on the basis. So it works this way. So it basically shifts them. Sigma x works on sigma, it basically shifts it to down state. Okay, and if you operate sigma z on down state, it shifts it to up state. Okay, these are two relations. This is the action of the sigma x on these operators. Okay, so now one of the questions will be here, how do I know this thing? How do I know this thing? So the answer to that is, we know it from here. I have written down it just like that without proving it, but we know it from the effect of because sigma x is also a rotation operator, and as a rotation operator, what it does is that you have only any basis you choose, only one of 3 sigma matrices will be, only one of the sigma matrices is going to be diagonal. Other twos, what is going to be their effect? Their effect is going to be shift. They are not going to be diagonal. If you do not have an operator which is diagonal in a basis, it means it is going to do the shifting. It's going to do some kind of a rotation, and we know these Pauli matrices are rotation matrices. They are going to do the rotation. Now if you have a situation where you have only just 2 states, the rotation, you can just take one state. Rotation means what rotation does, it takes one state, one vector into another vector. But if you have only 2 state vectors available to you, what will happen out of rotation? One vector will get transformed to the another vector. Then if you act on another vector, that will come back to the first vector. That is the only thing which rotation can do in a 2-dimensional Hilbert space, and that's what we see, that sigma x, because it is not diagonal, only sigma z is diagonal. So sigma x is basically rotating that basis. It is a rotation. If you have to see for yourself, this is what we are seeing is a rotation. Okay, because what sigma x is doing, it is rotating one vector into the another one, because that's the dimension of the space. And you can see it very clearly now if I just write it down here. So we will just get this stuff done quickly now. So we know here what we are going to get is that if we have up state and sigma, this we are going to get down state here. See, we are going to get down state, and that's going to give us 0. Similarly here we are going to get up state and then down, then we are going to get up state. Okay, similarly here we are going to get down and then we are going to get up state. Here we are going to get down and then we are going to get am I right everywhere? So here we are going to get down. So here we are going to get down and up state. Okay, that's going to be the matrix. Okay, so which means our matrix is basically, the matrix which we get is, this is 0 from orthogonality, this is 0, this is going to be 1 orthonormality say, so this is going to be 1 and this is going to be 0. That's what is our sigma x matrix. In the matrix representation, this is our sigma x. Okay, now you may think now as you can see that this matrix is not diagonal. In the basis which we have chosen, you choose any basis for polymatrices, only one of them, one of the polymatrics, it can be sigma z, it can be sigma x, sigma y, only one of them will be diagonal. You cannot have all of the three matrices diagonal. Okay, and you see, and one of them is diagonal and the other two are basically they are doing rotation on top of that. They are basically rotating that basis. That is the anyways effect of these polymatrices. Okay, now the another interesting thing is that we do not have to determine third one. Okay, we do not have to get and do the same exercise for sigma y. Why is it that? Because we use algebraic properties of this one. So one of the algebraic properties of them is that you can write sigma x, sigma y, iota times sigma z, or in other words, so this is sigma y and sigma y, so then I write sigma y and sigma x, which is going to be iota times this is z, there we have z and we have x here, and we have sigma z and sigma x, that's going to give me I times sigma y. This is another interesting set of properties of, this is part of that Clifford algebra which I was talking about. Okay, so polymatrices have these interesting properties, and if any one of you is interested in exploring this mathematically, I have written a very readable article about it, so I can refer you to that. So there I have given given explained detailed derivations of these properties, but we can have a separate discussion about how do we derive all these properties mathematically. How do you basically explore the Clifford algebra of polymatrices? Okay, so here I am just giving you these definitions that you can see this way. I mean, it's not, you don't have to accept him just like that. It follows from the fact that this one when you multiply, I mean, I would have written all these many properties about polymatrices. The commutation, if you just combine all of them together, like I wrote down a commutator for polymatrices, then I wrote down an anti-commutator for polymatrices. If you just combine all of them together, you will see this relationship which we have in front of us. They can be easily derived. There is nothing magical about it. Okay, but now what I am going to do is that I just want to say that because they satisfy a closed algebra. Closed algebra means if you know about sigma z and sigma x, it is easy to determine sigma y because they are part of a closed algebra. Understand? So therefore, what we can do, I mean, how do you? I will leave it as an exercise. What you have to do, you just do it for yourselves because I'm running slightly out of time. But it's very easy. Now, if I have to determine sigma y, what I'll do is that I will take this relation I sigma y and sigma z and sigma x. I'll multiply it with minus iota. Okay, so if I get minus iota, and on this side also I will have minus iota. Okay, so this gives me just sigma y. So sigma y is basically minus iota times sigma x, sigma z, and sigma x. Okay, and it's basically straightforward, simple algebraic, simple exercise here, that if we have to determine sigma y, what we have to do, you will just keep it there. We will have 1 and 0, 0 and minus 1, and I will have sigma x 0, 1, 1, 0. Fine. So if I just multiply it with minus iota, I am going to get 1 and 0, so it's going to give me 0. So here I am going to get 1. I'm going to get 1 here, 1 and 0. Here we are going to get 1, and yeah, I think this is 1, and here we are going to get -1, and then with 0. So if you multiply it, so we are going to get 0 minus iota and iota 0. I think that's our sigma y. That's how we determine sigma y. 0 minus iota 0. Okay, so that way we have got a full-fledged matrix representation of all the Pauli matrices. Okay, how do we get it? We basically use it the way, I mean, we use it in quantum mechanics. We get matrix. Same thing you can do for let's say angular momentum. Same thing you can do for harmonic oscillator. Like as we have creation and annihilation operators in harmonic oscillator, you can get matrix representation for them. And same thing works for Hamiltonian. I mean, if you have a Hamiltonian, you know the basis. Let's say you have a 3-dimensional basis, you will get 3 by 3 matrix, 9 elements, and the way you get it, you just basically take scalar product of that operator with the various basis elements. That's how you get it. But this is very important question in quantum mechanics, to get the matrix representation given a basis. And it's also interesting to note that any matrix, any operator in quantum mechanics does not have only one matrix representation, because the basis of any Hilbert space is not unique. You cannot just choose only one basis and you are done. Any Hilbert space has a various choices of basis, so you can always choose. That is why, that's the whole fun of doing. In the whole fun happens in quantum mechanics is something called a transformation. As I said, unitary transformations. What unitary transformations always keep on doing, they change you from one basis to another basis. That's where what's happening in quantum mechanics all the time. That's what the role of unitary transformations is in quantum mechanics. They always keep on changing the basis. Same operator, but you keep on changing from one basis to the another basis. Okay, and ultimately in quantum mechanics, we are always looking for that spatial basis, which is called eigenbasis. In our next lecture, we will get to that. Why is that eigenbasis, eigenvectors, eigenvalues, why are they important? Why is it that we are always looking for them? What is so special about them? But in today's session, I think I wanted to give you a kind of a hang, so that you get a sense of why Pauli matrices are fundamental. And given the fact that they are fundamental, then how do I play around them, so that I can make a sense of why are these matrices. And I think one important thing I told you about is the Clifford algebraic aspect of Pauli matrices, and the fact that Pauli matrices are not just tied to spin. You can just take them away from spin, and you can just, anywhere you have this 2-level system, anywhere you have double degeneracy, you can always, Pauli matrices will always come in. You don't have to bring them in, they will always come in. So you can just take Google today in quantum, you can just Google and 2-level systems in quantum mechanics, and just look at their mathematical formalism. You will see Pauli matrices abundantly in quantum mechanics. You will see them everywhere. So I think that on that interesting note, I will we'll stop. We'll see if it seems there are some questions. So we'll take them those questions, and I think that's for Pauli matrices. So we will, if some of you are interested, then we can have a separate session on Clifford algebra, because as I said, it's very important. But that will not be just part of our quantum mechanics course, because it will take us towards mathematical physics. Okay, so but we will do some exercises to understand these Pauli matrices better in terms of quantum in quantum mechanics.